11s and grade 12s. In today's video, I'm going to be doing Newton's law of universal gravitation. In this playlist, I have also covered Newton's first, second, and third law. I do past paper questions. I give teacher tips throughout all of my videos because I am a matric teacher. I set and mark matric exams, so I know exactly what you need to do in order to level up your marks. I hope that you watch throughout the whole video to find those teacher tips, and I hope you subscribe for more physics and chemistry videos. Let's go. Newton's law of universal gravitation is unlike the other three Newton's laws that we've learned so far. Remember Newton's first law of motion, F net equals 0. Newton's second law of motion, F net equals ma. Newton's third law of motion, we didn't do any calculations, but you need to know the definition. Links to these three laws in the description box below. Newton's law of universal gravitation has two new unique formulas that you need to know about. Now, what I've done for you guys is I've copied and pasted what the exam guidelines say with regards to Newton's law of universal gravitation. This is for the grade 11s and for the grade 12s. This is exactly what you need to know for your exam. So you need to be able to state the definition, solve problems using this formula. It doesn't mention the other formula, but you need to be able to apply the other formula as well, which I will show you how we derive it. You need to describe a lot of other terms, distinguish between things like mass and weight, and calculate the weight of an object on a certain planet. These are the two formulae that we are going to use when we come to Newton's law of universal gravitation. G is a constant, m is mass. This is referring to distance between centers. F is a force, and this is gravitational acceleration. I will go through all of these, but just take note that your formula sheet will mention these formulas. I took a screenshot of this, so it comes directly from your formula sheet. Please note that these are basically the same formulas. It's just that instead of D, they use R. Some people prefer using D, some people prefer using R, but they mean the same thing in the context of these formulas. And same thing with these two. Same formulas, it's just a D versus R situation. It depends on what your teacher uses, what you prefer. They mean the same thing. So I will show you how we get from this formula to this formula, and I'll also show you in which circumstance we use which formula. But let's first go over the different definitions that you need to know. So first of all, you should know that masses exert a non-contact force on each other. So anything that has a mass will exert a force on anything else that has a mass. It's a non-contact force, which means the two things don't have to be in contact with one another. And gravitation is one of these forces. It's a force of attraction of masses. So the force of gravity, that's why we fall towards the ground while we fall towards Earth. Okay. And this size of attraction, or in our case, we're speaking about gravity, the size of the force of the gravity between the two objects depends on the mass of each object and the distance between their centers. You will see this concept, distance between their centers, a lot, especially when we look at the definition, but we need to consider two objects. And when we consider the force that object A exerts on object B, or that object B exerts on object A, we measure that force by looking at the distances between their centers. We always measure from the distances between their centers. But before we get to the definition for Newton's law of universal gravitation, I just want to remind you about the definition for weight. Remember, weight is the force of gravity. So that is the gravitational force. It's the force of gravity. And this, as I wrote here, is the metric definition. Weight, the gravitational force that the Earth exerts on any object on or near its surface. Please remember that weight is very different to mass. So weight is a force. It's the gravitational force. It's measured in Newton. Mass is the amount of matter in a body. It's measured in kilograms. It's a scalar. To get from one to the other, we use this formula over here. The weight of an object is equal to mass times gravity. Or you could say Fg equals mass times gravity. Exactly the same thing. On Earth, G is 9.8 meters per second squared. And here's a very basic example of how to calculate the weight of something with a mass of 800 grams. Just remember that mass must be in kilograms. That's why I converted it over here. Please, it's very important to know the differences between mass and weight. And according to exam guidelines, you also need to be able to explain weightlessness. Now, weightlessness of an object is basically a sensation. We only feel a sensation of weightlessness, not
true weightlessness. And it basically happens when the only force acting on our body is gravitational force, free fall. So if we jump off of something or whatever, then we'll experience a sensation of weightlessness. So an object is weightless if it is somewhere in the universe where the gravitational field is zero. That is how you would explain weightlessness. And it's a sensation. Now, here is my definition for Newton's law of universal gravitation. And you see how I said important. They are very, very likely to ask you this definition. Either going to be this definition or it's going to be Coulomb's law, which is a very, very similar definition. And if you've done electrostatics already, you should be thinking when you see the definitions for Newton's law of universal gravitation, when you see this, you should be thinking, that looks very similar to Coulomb's law. This is Coulomb's law, by the way, if you have forgotten or if you haven't done it yet. Can you see the similarities between this and this? Well, if you do, then you will also be able to see the similarities between the Coulomb's law definition and the Newton's law of universal gravitation definition. They're very likely going to ask you one of the two. So, Newton's law of universal gravitation, it says every body in the universe, so everything with a mass, attracts every other body with a force. So, I have a mass, I am a body, I attract my calculator. It has a mass. So each body in the universe attracts every other body with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Now, grade 11s and grade 12s, it's very important for you to get this definition correct. Because if you, for example, leave out the word product of, you are saying the wrong thing. Because look at the definition and look at our formula over here. I want to show you that the definition and the formula match up. So each body in the universe attracts every other body with a force that is directly proportional to the product of the masses, directly proportional to the product of their masses. Now, product means multiply. That's what product means. You multiply the masses together. And as you can see in the formula, I'm multiplying the masses of the masses together, product of masses, and inversely proportional to the square of the distance between their centers. Inversely proportional to the square of the distance between their centers. So you can see here that the distance between the centers are squared. So if you leave out square, definition is wrong. If you leave out between their centers, definition is wrong. And remember, I mentioned that we have a mass. We always use the distances between the object's centers. That is what R is. Or D. You can call it R, you can call it D. But you just need to know the definition. You need to get it correct, please. Now, directly proportional means that if one thing goes up, the other thing will go up. So if mass increases, the force will increase. So if the mass of one object increases, the force increases. So if the mass doubles, the force will double. If the mass of object 1 and the mass of object 2 both double, so say I times this mass by 2 and I times this mass by 2, the force that the one object exerts on the other object will be times by 4. That's very important. That's what direct proportion means. If one quantity goes up, the other goes up by the same proportion. If the one goes down, so if I halve the mass, the force decreases. And this should make sense. If you have a big object and a big object, they're going to have a stronger force of attraction than if I have two small objects. If I make the one object bigger, the force of attraction will be bigger. And think about the distance. If I have two objects and they're very, very far apart, the forces that they exert on each other is going to be small. But if I move those objects closer together, they're closer to each other, that force of attraction is going to be bigger. So as I make the distance smaller, small distance, big force of attraction. And that is why we say that they are inversely proportional. So inversely means the opposite. So if R gets very big, the force gets small. Or if R gets very small, the force gets very big. And I hope that you guys know that this is just how we represent direct proportion relationships. So the force is directly proportional to the product of the masses. And when we say 1 over, that represents inverse proportion. So the force is inversely proportional to the square of the distance. So you should know, if I represent it on a graph, this is what a direct proportion relationship looks like. If I represent this on a graph, this is what an inverse proportion relationship looks like. And if I do this, so if I do the reciprocal of r squared, so I go 1 over r squared, then that will straighten out into a directly proportional relationship. Obviously, that line must be straight. A directly proportional relationship. So the force is inversely proportional to r squared, but the force is directly proportional to 1 over r squared. Another very important concept to understand is that because of Newton's third law of motion, the force that the mass 1 exerts on mass 2 is the same as the force that mass 2 exerts on mass 1, but in opposite directions. So think about the blue object. The blue object is pulling mass 2 to the left. So mass 1 exerts a force on mass 2 to the left. Okay, the blue object is pulling the green object to the left. The green object is pulling the blue object to the right. So mass 2 exerts a force on mass 1 that goes to the right. These forces are equal in magnitude but opposite in direction. Okay? So mass 1 and mass 2, they exert an equal but oppositely directed force. Now remember, I showed you guys this formula that is currently on the screen, and I said that there's another formula that we may have to use. And that additional formula looked like this. And I said I will show you how to get from the one formula to the next. So starting with this formula, I'm going to quickly show you how we get the second formula. Let's pretend I'm taking a scenario where I want to calculate the force that the pen exerts on the earth and the force that the earth exerts on the pen, the gravitational force. Because remember, pen and earth, they're both bodies, they both have a mass, so they exert a force on each other. Now, I hope that you guys know that the force that the earth exerts on the pen is also called the gravitational force or weight. And how can I work out the gravitational force or weight? I can say mass times gravity. So instead of writing the force, F, which would be the gravitational force, I'm going to write mass times gravity. And remember, that would be the mass of the pen. So I'm going to call it mass of pen. Remember, M1 is my mass of my pen, M2 is my mass of my earth. So I've got mass of my pen times gravity. That will get me the force of gravity. Okay, if I carry on writing that formula, I hope that you know, according to maths, that if I've got mass of pen on this side and I've got mass of pen on that side, I can cancel them out. I'm basically dividing each side by mass of pen. And look at what I'm left with. I've got G is equal to big G, mass of earth, divided by r squared. And this is my second formula. Remember, I showed you my second formula goes G is equal to big G, mass over r squared. Now, what I want to show you is that G is gravitational acceleration. So on Earth, that value is 9.8 meters per second squared downwards, right? Big G is a constant. We get that on a formula sheet. The mass of the pen cancelled out. This is the mass of the Earth. And that is the distance between the two objects. So what this formula is showing is that the gravitational acceleration is always dependent on the bigger object. Not the little mass of the pen, but the bigger object. And if I want to work out the gravitational acceleration on a certain planet, I don't use the mass of the smaller object on the planet. I use the mass of the planet itself, the bigger object. That's going to be very important later on. So although you may not completely understand it now, I just want you to keep that in mind. Another thing, if you do not understand how I got from the first formula to the second formula, I don't want you to stress. All that I want you to know is when to use which formula. So we will use this formula when we're working out a force that one object exerts on another. So for example, if the question says, work out the gravitational force, or work out the force that planet A exerts on planet B, or the force that Mars exerts on Earth, or so on or so forth, you'll use this formula. You can also use this formula to work out a distance that they require. So for example, work out the distance between the satellite and the Earth, or the man standing on the surface of the Earth and the Earth itself. So we could also use that formula. The one above we use in order to work out gravitational acceleration, which is g. That's measured in meters per second per second. And when we use this formula, we only use the mass of the bigger object. So for example, if you have Mars and you have an astronaut standing on the planet of Mars, and they want to know g for Mars. Remember, g for Earth is 9.8 meters per second squared. But if they want to know what is the gravitational acceleration for Mars, and they give you Mars, the mass of Mars, and they give you the mass of the astronaut, we don't care about the mass of the astronaut. We only care about the mass of the bigger object. And that's basically what all of this says here behind me. So it says that g, so gravitational acceleration, on Earth it's 9.8. That doesn't matter. It doesn't depend on the object's weight. So if I drop a very light pin versus a massive bowling ball, in the absence of air friction, they should both hit the ground at the same time, technically, if there's no air friction. And that's because g is the same for both of them. So gravitational acceleration for the pin, gravitational acceleration for the big bowling ball is 9.8 meters per second per second. And the way that we calculate g is by using this formula over here. So the one above me, and the mass that we use is the mass of Earth. So take note how when I'm working out gravitational acceleration for the pen, the very light pen, or the very heavy bowling ball, I don't care about their masses in this formula. All that I use is the mass of the Earth. And that's why g is the same for all objects. So I'm going to show you an example of a question where I use the one formula, an example of a question where I use the other formula. You will see the differences. So the question behind me, it says, first of all, define Newton's law of universal gravitation. That's a definition. That's something you're going to get full marks for. And here's the definition over there. That's exactly what you will say. But now let's look at the question itself. We've got mass P and mass Q, and they give me a distance of 80 centimeters between their centers. It's important that they're going to give you the definition between their centers. It's also important to note that in my formula, F equals big G m1 m2 over r squared, my distance must be in meters. So I need to convert this to meters. How do you convert centimeters to meters? Well, there's 100 centimeters in 1 meter. So I need to divide by 100, and we're going to get 0.8 meters. Converting is a very first important step always in our physics questions. So we've got our r, that's the distance between their centers. We've got the mass of object 1. We've got the mass of object 2. They want to know the gravitational force that P exerts on Q. Okay, the gravitational force. So as soon as you see the gravitational force, you know you're going to do this formula over here. m1, m2 over r squared. Remember, you can use d squared. It means the same thing. It means the distance between their centers. G is a constant, which means they give it to you on the formula sheet, and it's always going to be the same thing. Mass of object 1 is 55. Mass of object 2 is 70. Obviously, it doesn't matter which way you write that. The distance between their centers is 0.8, and please don't forget to square it. A lot of my students always forget to square this, and they lose marks. Now, my calculator gives it to me as 4,012. So I'm going to round it off to 2 decimals. So 0.1 times 10 to the negative 7 Newton. Remember, force, the unit for force is Newton. And also, you can't leave off the times 10 to the negative 7. That's part of the answer. It actually means, and I wrote it over here, that my answer is 0.00000400124 newtons. That's what that means. And let's just remember, the question said the force that P exerts on Q. So P exerts on Q. So what does P do to Q? Well, it will pull Q this way. P will exert an attractive force on Q. So your direction over here, you can say attractive because it's an attractive force, but I would say attractive and in particular to the left. Think about it. They're asking about the force that P exerts on Q. So what does P do to Q? It pulls Q to the left, and that's your answer. The next question says, what is the gravitational force that Q exerts on P? Notice how they just swapped the two objects around. So that's an easy answer. Your answer will be the same. So it'll be 4,01 times 10 to the negative 7 newtons attractive to the right. So if P exerts Q to the left, Q exerts on P to the right. Same magnitude, opposite in direction because of Newton's third law of motion. So that's an example of a question where you use this first formula over here. But what about this formula over here? Well, let's take a look at a question that could ask you to use that formula. Something like this. Calculate the acceleration due to gravity. So we're looking for baby G. Acceleration due to gravity on planet Mars, which has a mass. So they give me the mass of Mars and a radius of this. So we have Mars. Mars has a particular radius, and we want to know what is the acceleration due to gravity on Mars's surface. So the radius of the planet is the distance between the centers that I'm looking for. Now, to make this question more difficult or to throw you off, they could give you an additional mass that does not matter. So for example, they could say that there's a box standing on Mars and the box has a mass of 10 kilograms, and they could ask you for acceleration due to gravity. Remember, acceleration due to gravity, we calculated using this formula. And the only mass that I care about is the mass of the bigger object. So I don't care about the box standing on Mars. I care about the mass of Mars itself. So if I'm looking for acceleration due to gravity on Mars, I use the mass of Mars. If I'm looking for the acceleration due to gravity on Earth, I use the mass of Earth. G over here, that's my constant. It's the same as what we did in the previous question, 6,67 times 10 to the negative 11. Remember, that will always be given on your data sheet, so you don't have to stress about that. The mass of Mars is 6,42 times 10 to the power of 23. And the radius of Mars is going to be the distance between my centers. That is 3,4 times 10 to the power of 6. Remember to square it. Please, please, please. R is squared, so you must square this. And I get 3,7. Now remember, gravitational acceleration is measured in meters per second squared, meters per second, and your direction is towards Mars. You can say towards the center of Mars, towards Mars, but something about towards Mars because it's downwards, but downwards isn't really correct because, I mean, if an object is here, it'll be pulled towards Mars. Towards Mars. It's towards the center of whatever planet we are talking about. I hope that has been helpful in terms of Newton's law of universal gravitation. In future videos, I will be looking more closely at the relationship in this formula and what happens if I double the distance or quadruple the distance. What does that do to force? I'll also be looking at more past paper examples, so I hope to see you in those videos. I hope you subscribe for more physics, more chemistry. Goodbye, everybody.